So orthogonality in inner product space, so what is that? Let X be an inner product space and X comma Y belongs to X. We say that X is orthogonal to Y if X inner product with Y is actually 0. Okay. Note X is orthogonal to Y if and only if Y is orthogonal to X. X is orthogonal to Y if and only if X with inner product Y is 0, and this will happen if I will take bar both the sides is equal to 0. That means Y inner product with X is 0. That means Y is orthogonal to X. Okay. Note 2, 0 is orthogonal to Y for any Y belongs to X. 0 Y, we can write 0 plus 0 Y. That can be written 0 Y plus 0 Y. So we have 0 Y is equal to 0 Y plus 0 Y. That means this will be cancelled out. I can add 0 also. That means 0 is equal to, okay. So this implies 0 is orthogonal to every element X in Y, Y in X. Okay. Note 3. If X is orthogonal to Y and Y is orthogonal to Z, it does not imply X will be orthogonal to Z. Sorry, 1 minute. Convention. If X is orthogonal to Y, we denote it by X orthogonal to Y. This symbol. Okay. Since X is orthogonal to Y if and only if Y orthogonal to X. So X so X we simply read it X and Y are orthogonal. Because we know that if X is orthogonal to Y, Y is also orthogonal to Y. So simply do not say X is orthogonal. You simply say that X and Y are orthogonal. Okay. So note 3. If x is orthogonal to y and y orthogonal to z, it does not imply that x will be orthogonal to z. Solution. You see, I am taking x is equal to 1, 0, 0 and y I am taking 0, 1, 0. So x is orthogonal to y. Okay, because okay. So z I am taking minus 1, 0, 0. Then y is orthogonal to z also. But x is not orthogonal to z. Okay, definition. Let M be a non-empty subset of an inner product space X. Okay, net product space X. Okay, we say that M is an orthogonal set in X if X is orthogonal to Y for all X and Y belongs to X. Sorry, X Y belongs to M. X not equal to Y. Okay. No, since 0 is orthogonal to for all X belongs to M, then then 0 can belongs to M also. Okay, 0 can belongs to M also. So this is not for. Okay, so theorem. Let M be a non-empty subset of an inner product space X and 0 does not contain in M, then M is linearly independent. Linearly independent. Let's see its proof. Let x1, x2, xn belongs to M such that alpha 1 x1 plus alpha 2 x2 up to alpha n xn is 0. Okay. Then for I goes to 1 to n, we have we have alpha I is equal alpha norm xi का square is equal to alpha I alpha I L xi that we can write alpha 1 x1 plus alpha 2 x2 alpha n xn xi because xj xi is 0 for but j is not equal to I. So this implies alpha xi norm square. The value of this is 0, but 0 is orthogonal to everyone. So this implies alpha I. Since 0 does not belongs to M, so this implies xi is non-zero. So this implies norm xi is non-zero. We get alpha I is equal to 0 for so this implies M is linearly independent. Okay. Definition. Let M be a non-empty subset of an inner product space X and X belongs to X. Then X orthogonal to Y, we mean that X is orthogonal to Y for all Y belongs to X. Okay. Definition. Let M and N be two non-empty subsets of an inner product space X by M orthogonal to N. We mean that X is orthogonal to N for all X belongs to M. That simply mean that X orthogonal to Y for all X and Y for all X belongs to M and Y belongs to M. Okay, so proposition. Let M be a non-empty non-empty subset of an inner product space X, then M perp is called orthogonal complement of M in X and is defined by M perp is equal to collection of all such X which is orthogonal to Y for all Y belongs to M. Sorry, let's say definition. Okay, definition. Orthogonal complement definition. Okay, so theorem, let M be a non-empty subset of an inner product space X, then M perp is a closed closed vector closed vector subspace of X. In other words, M perp is a closed normed subspace. The closed inner product subspace of X. Okay, let's see its proof. M perp means collecting X belongs to X such that X is orthogonal to Y for all Y belongs to M. Since 0 is orthogonal to Y for all Y belongs to M, that means 0 belongs to M perp. Okay, so this implies M perp is non-empty. Okay, so let X and Y, X1 and X2 belongs to M perp. Alpha and beta belongs to field K. Then as x1 and x2 belongs to M perp implies x1 is orthogonal to y for all y belongs to M. That means x1 y is equal to 0 for all y belongs to M, and x2 is also orthogonal to y for all y belongs to M. That means x2 y is 0 for all y belongs to M. Okay. Now alpha x1 minus beta x2 y. Now for y belongs to M, we have That means alpha x1 y minus beta x2 y. That means alpha into 0 minus beta into 0. 0 minus 0, that is 0. So we got alpha x1 and beta x2 is equal to 0 for all y belongs to n. So this implies alpha x1 minus beta x2 is orthogonal to y for all y belongs to n. So this means alpha x1 minus beta x2 belongs to M perf for all x1, x2 belongs to M and alpha beta belongs to field K. So this implies M perf is a vector subspace of X. Okay. Now M perf is closed. Okay. Let Xn be a sequence in M perf such that Xn converging to X in X. Since okay, since Xn belongs to M per for each n belongs to n, we have Xn is perpendicular with orthogonal to y for all y belongs to m. That means Xn y is 0 for all y belongs to m. Let y belongs to m. Then x y is nothing but limit of xn y, the limit and tending to infinity and tending to infinity. This is 0, so this will be 0. So this implies x y is 0 for all y belongs to m. That means x belongs to m part. So this implies m part is closed. Okay. Okay. So M perp is closed. So today's lecture up to this.